Okay. Yeah. It worked.
Do you hear me? Yeah. Okay, hello everyone, and welcome to the last session of the day. So we'll start this session with a presentation of Rembam, which will be done by Jakub Belenki from Fortify IQ. I leave the floor to you.
Okay, thank you for the introduction. And everybody, welcome to the presentation of Rembam, a scheme for protecting Aes against side channel attacks. I'm Jakub Belenki from Fortify IQ, and we have a booth in the presentation hall. So if you have any questions regarding the presentation, you can ask us there. The scheme which I am presenting today is the development of the Fortify IQ research team to which I belong. Let's start with a brief review of history of Aes. In 1997, NIST announced an Aes competition. Among the design goals of the competition, besides the security, were computational efficiency and low memory requirements. While Rindel selected as Aes is compact and fast in hardware implementation, it is highly prone to the side channel attacks. And that's why the academic research of ways to protect it against side channel attacks started immediately after the standard was adopted. A lot of the protection schemes suggested in academic papers were later broken. Some of them were not broken. I mentioned some of them. Two of them, threshold implementation, known as TI, and domain-oriented masking, known as DOM, represent the Aes state as XOR of several shares. And they perform the computation in such a way so that under reasonable assumptions, it is possible to prove that no information can be extracted by side channel analysis up to a specific order. The higher the order is, the more shares are required. In order to prevent possible leakage through glitches, in these approaches, it is impossible to reach low latency because the complexity of the computation during any clock cycle is severely limited. Another approach is dual rail with pre-charge logic, which was recently improved in a paper by Zastrich and presented at CHESS 2020. And with this recent improvement, in this approach, it is possible to achieve low latency, 1 AES round per clock cycle, but the dual rail and the pre-charge logic take up substantial chip area, and the critical paths are long. So there are schemes which provide high security of AES against side channel attacks. Some of them have low gate count by high latency. Others have low latency, but a significant gate count. The big challenge is thank you. Yeah, the big challenge is to combine high robustness against side channel attacks. There are schemes which provide high latency, high security of AES against side channel attacks. Some of them have low latency but a significant gate count. Others have significant gate count, low gate count, but high latency. The big challenge is to combine high robustness against side channel attacks with both low latency and low gate count. The topic of this talk is how. We took a different approach. Let's start from the high level, and in the next slides, we'll see more technical details. Aes transformations are defined in a specific algebraic structure. The central idea of random is to randomize the input data and the key by switching to a larger algebraic structure in which each value of a byte has many different representations. We perform all the computations in this larger structure, which we call redundant domain. The following picture illustrates the intuition behind the idea. The yellow point is the average power consumption related to a specific byte of a specific intermediate result. And the orange point is the power consumption in the case of a specific value of the byte. This is in a standard AES implementation. In the redundant domain, the same clear value has many redundant representations, and their average, which is the green point, is much closer to the overall average, meaning a lower side channel leakage. In our experiments, we see that the leakage decreases very rapidly, approximately exponentially, as a function of the redundancy. That is, of the number of additional bits in the redundant representation of each byte. For redundancy 8 with 16 AES boxes, no signs of leakage were observed up to 350 million traces. Now let's switch to the technical part. In the standard AES, we see each byte as a polynomial over GF2, modulo a specific irreducible polynomial of degree 8. Let's call this polynomial P0, 11B. The redundant domain is a finite ring, which is an extension of this field, and its elements are seen as polynomials modulo PQ, where P is an irreducible polynomial of degree 8, which may or may not be equal to P0, and Q is a polynomial over degree D. The degree D is the security parameter of the scheme, and it is the number of additional bits in the redundant representation of each byte. In order to switch to the redundant domain, two transformations are applied to every byte. First, a linear transformation from the polynomial basis of a root of p, 0, to the polynomial basis of a root of p. And second, the addition of the a multiple of p of a degree up to 7 plus d. So we switch to the redundant domain, and all the computations are performed in the redundant domain. Finally, each byte is de-randomized by reducing its modulo p and switching back to the standard basis. We'll call this composite transformation the canonic homomorphism. Let's look at the transformations used for the AES encryption. Add round key in the redundant domains remains XOR. Shift rows remains permutation of redundant bytes. Mix columns remains multiplication by a fixed matrix 4x4, or only the matrix coefficients must be represented with the in the correct basis. The only non-trivial case is the only non-linear transformation, which is substitute bytes as box, and it deserves a separate slide. In AES, the S box is defined as the inversion in the a composition of the inversion in the field where 0 is mapped to 0 with a specific affine transformation. Raising to the power of 254 is equivalent to the inversion, and it works for 0 as well. In the redundant domain, in order to invert a byte by raising to the power of 254, we perform a series of 7 transformations shown here. 4 out of 7 transformations are multiplications, shown in red, and 3 of them are shown in blue, are raising to the power of 2, power of 4, and power of 16, which in a ring of characteristic 2 are linear. Finally, instead of the standard affine transformation, in the redundant domain, we perform another affine transformation homomorphic to the standard one under the canonic homomorphism. After each one of the 7 transformations, multiplications and linear transformations, the result is re-randomized by the addition of a random multiple of p. This re-randomization increases the number of possibility for each multiplication from 2 to the power of d to 2 to the power of 2d, which is a huge increase. Besides, without the re-randomization, some of the intermediate results of raising x to the power 254 inevitably are x to a power which is not coprime with 255, the order of the group, and raising to such a power is not invertible, and therefore the space of the representations shrinks even to a value lower than 2 to the power of d. In the paper, we show both experimentally and theoretically that without re-randomization, the leakage is much more significant. Now, about the number of random bits used for this re-randomization. In our experiments on the NFPGA board, we saw no difference in leakage between 2 cases. The case of unit set of random bits per byte per round, and the case of the reuse of random bits as long as two conditions hold. First, 7 different randoms are used for 7 different stages, shown here. And second, these 7 randoms are rotated at every clock cycle so that no random is used at the same physical gates at 2 consecutive clock cycles. The reuse of random bits makes the number of random bits per AES encryption significantly lower than in all other schemes that we are aware of. And this is very important for practical use of the scheme. Another aspect of rambam is an inherent protection against CIFA. In this aspect, it is similar to TI and DOM, which have inherent protection against CIFA1, that is CIFA with target in registers, not in the combinational logic. Both TI and DOM are resistant to CIFA1 up to a simultaneous fault in several bits of the state in an amount equal or greater to the number of shares, for obvious reason. If the number of bits is less than the number of shares, that this set of bits bear no information about the clear data. In the case of rambam, there are many sets of bits which bear no information about the clear data. The minimal number of bits of the state which can possibly bear information about the clear data depends on the polynomial p and the redundancy, and in general, it grows with the redundancy. We chose redundancy 8 as the primary target of our research, since it provides a high level of security, as we will show. For redundancy 8, with appropriate polynomials p, all sets of 4 or less or more bits, 4 or less bits, bear no information regarding the clear data. So a simultaneous fault up to 4 bits is not enough for a successful CIFA attack. Most suggested TI and DOM implementations use at most 4 shares. So the same similar upper bound in the case of TI of DOM is at most 3 bits. In the independent evaluation of the rambam protection scheme by a common criteria lab, I will speak about it later, not only CIFA1 attacks, but also CIFA2 attacks on the combinational logic were unsuccessful. To evaluate the robustness of rambam against ion channel attacks, we performed experiments on an FPGA board. Using chip whisperer for power consumption measurements, using the zero test of the TVLA methodology. Here you see the graphs of the maximum absolute value of the t-test over the timeline, up to 1 million traces, up to for the redundancy values between 3 and 8 in a logarithmic scale. You can see the approximately exponential decrease of the t-test as a function of the redundancy, and no signs of leakage for redundancy 8 were observed. Actually, for redundancy 8, we performed additional experiments up to 5 million traces, and still there were no signs of leakage. This graph relates to a compact implementation with 1S box. A similar analysis for a fast implementation with 16 S boxes and 1 clock cycle per round showed absolutely no leakage to up to over 350 million traces. The multivariate second order t-test for redundancy 8 in both the compact and the fast implementation also showed no leakage. Let's summarize the experimental results for redundancy 8. Security-wise, no leakages were found for first and second order t-tests, including multivariate. Latency-wise, it is 12 clock cycles per AES 128 encryption in the fast configuration, just like typical unprotected implementation, and like the implementation by Zastrich and others presented in CHES 2020. It is much lower than in TI and DOM implementations, which have at least 246 clock cycles per AES encryption. Sorry. Even the compact implementation with 1S box and low latency, and also has low latency and also a higher throughput per gate than TI DOM implementations. Regarding the chip area and the maximal clock frequency for the fast implementation of rambam, Here is a table comparing between random and the paper by Zastrich and others. You can see that random has a significant advantage in the area, the maximum clock frequency, the throughput per area, and the number of random bits per AES encryption. Besides our in-house research, an FPGA implementation of random with redundancy 8 and 16 AES boxes was recently evaluated by one of the top common criteria labs using analysis methods used for the highest level evaluations. And here are the results. The t-test analyses, first and second order, univariate and multivariate, were performed on over 30 million traces. No leakages were found. Template attacks on both the first and the last rounds, with different sets of points of interest, were performed with 15 million traces for the profiling stage and 300,000 traces for the attack stage. The mean rank of the correct bytes of the key was close to the median rank 128, and no bytes of the key were found. All attempts of CIFA attack failed. Let's conclude. Random is a practical, purely algorithmic defense of AES against side channel attacks and CIFA, independent of the underlying technology. It combines a high security level with both low latency and low chip area, and can be implemented in many different configurations. The number of random bits per AES encryption is significantly lower in random than in other schemes. Compact configurations with one AES box fit the needs of the IoT devices. Fast configurations with a latency 12 clocks per cycle, 12 clock cycles per AES encryption, optimally with multiple pipelines, provide ultra-high bandwidth while taking up relatively low chip area. There are also fast implementations in software. Thank you for your attention.
So does anyone have any question?
Thank you. Thank you for your presentation. Just a small remark on your slide, on slide 10. I'm here.
Yeah.
In front of you. On slide 10, you say that Avavan 5 corresponds to EL7. That's wrong. But anyway, we can talk later about that if you want. And my question is, have you considered combined fault and side channel attacks?
Sorry?
Have you considered on your implementation what we call combined attacks, where you combine a fault and side channel techniques in the same attack?
What I wrote here, I took from the table in the common criteria document, which lists the levels of Avavan needed for different EALs, and Avavan 5 is listed for levels 6 and 7.
I can try to be more technical in my question. Your fault detection mechanism with the redundancy, it triggers at as soon as I inject a fault, or during the next clock cycle, at the end of the round. Where can you explain a bit how it works? Or does the computation goes until the end of the AES computation, and then there is a checking if there is a fault or not? I'm not clear now.
Are you asking about how the common criteria lab performed the fault detection?
No, that was the first remark. My question is about the fault mechanism, the fault detection mechanism in your proposal. You said it's a redundancy with some bits about the original bytes, and I was asking how it when the fault detection mechanism is triggered at the end of a clock cycle, at the end of a AES round, or at the end of the encryption.
No, I claimed no fault detection, and actually fault detection would not help against CIFA. What I claimed is that up to a specific number of bits, which depends on the polynomial p and on the redundancy, any set of n bits bears no information regarding the clear state, and therefore any CIFA attack which targets simultaneously less than a specific number of bits cannot possibly be successful. That's what I claimed. There is no fault detection.
Okay. Okay. Thank you.
I have a question here. You know, we are a bunch of theoreticians here, and we love to see the proofs. In addition to practical experiments that you have here, can you provide some kind of proof for the security of the underlying scheme? Because you compared your scheme, for example, with TI, with DOM, with LMDPL, and so on, and most of them have some security proofs, right? Considering adversary model like, let's say, probing security model, and then you can provide some proofs that their scheme is, for example, first order secure. What I have seen from your scheme, what I have understood, you're probably actually using some kind of a code-based masking scheme. Means that you change the 8-bit value to another larger field and then add some kind of a noise to the code. I mean, the noise is recoverable. And then of course, you change all the computations for the SPOCs, for the mixed column, and so on. But I'm not sure actually how you can prove the security of this, because when you change the field from 8-bit to another larger field, then for every single 8-bit value, you have a couple of other possibilities. For example, you increase, I think, from 8-bit to 16-bit with 8-bit redundancy. Then I don't know how many possibilities you have to represent that 8-bit value. And then if it's, and then the entropy of this plays an important role. I mean, but just, let's say, measuring the sergeant leakage of the design or implementation, and then arguing that it's secure, of course, it's practically secure, and we really appreciate that. But as I said, I mean, many theoreticians would love to see the proofs that whether you can provide any proof for that, because, you know, the implementation of one scheme can be very, I mean, you can make something which is secure in practice, but there is no guarantee that if somebody takes your code or your implementation and put it in another device or another FPGA, another platform, or another ASIC, then it provides exactly the same result. But if you have provable security, you can have a level of confidence that this may happen. Okay, but the last question, I mean, we are all out of the time already, but just as last question, you have for the one SPOCs version of your design, you have very low number of measurements, right? I mean, 5 million compared to 350 million. Does it mean that if you measure longer or more in a one SPOCs version, you see the leakage?
No, in fact, we never saw a leakage. We just at 16 SBoxes, it goes much slower. So that's the number of traces we actually did, and there were still no signs of leakage. We didn't measure anymore. Now back to your previous question regarding the proof. Well, first of all, as you saw, we don't claim that there is no leakage. There is a leakage, and we show how it decreases with the growth of redundancy, but it exists. So we don't have a proof similarly to TI and DOM. By the way, you yourself in an article from 2018 showed that the assumptions under the proof work only up to a specific number of tens of millions of traces. So behind beyond this value, actually the proof, the assumptions of a proof not necessarily hold. But yes, we have no proof. We are working on presently on another version in which we are going to provide the proof. But in this version, we have no security proof, only experimental results and some theoretical analysis, which is not a proof.
Okay, thank you. And we can thank the speaker again. So the next talk will be given online by Fan.
Yes. Are you going to play the video?
Yes, you can go whenever you want. Or maybe you had a video or...
Yeah, we uploaded the video already.
Okay. He uploaded the video. You want to play the video, right?
Yes, please.
Okay. Then let's go.
Hello, everyone. My name is Fan Zhang, coming from Zhejiang University, China. This is joint work done by my student Chen Xiang, Ziqi, and Professor Kui Ren, and other colleagues in Zhejiang University. This paper proposes a new analysis method combining algebraic and persistent fault analysis. First, background. Fault attack was first proposed by Dambonnet in 1996. It is an active attack and has two stages: the online fault injection stage and the offline fault analysis stage. The pair of correct and faulty ciphertext can be used to explore the secret key. The adversaries need some equipment to generate non-invasive, semi-invasive, and invasive injections. Possible injection methods can be clock glitch, voltage glitch, EMFI, and laser FI. Most of fault injections that are studied are actually non-invasive attacks. When we talk about the fault attacks, we need to address the so-called fault models, such as the fault width and the fault type. Also, we need to address the fault location and timing. Fault location means in which byte or nibble the fault is injected, and the timing means in which round and which operation the fault is injected. Because most of the faults are transient, means a short time, fault attacks always require very precise timing. This is harder for those who launch the attack. In CHESS 2018, we proposed a new type of fault called persistent fault, which can last for a couple of rounds or incursions. We assume the adversary can inject faults before the incursion of a broad cipher. For example, he can alter the S box in AES. The injected faults are persistent for multiple incursions. The adversary is capable of collecting multiple ciphertexts, and the watchdog counter is not considered in this case. The core idea of persistent fault attack is that the previous tightly coupled fault injection stage is now partitioned into two stages: the loosely coupled fault injection stage and the subsequent incursion stage. So in total here, we have three stages. The interesting part of PFA is that the fault is persistent in the S box. However, the faulty element of S box, for example, 61 here in the red, may not be accessed. Some ciphertexts are correct, some are incorrect. So how to do the simple persistent fault analysis? Suppose the correct element is V, so after the injection, it's V star. For a specific ciphertext byte, V star will appear twice here, and we will never see the original V. So the distribution of the values of that ciphertext byte is now becoming biased. So the adversary can exploit the three types of fault leakages: for the zero probability and the maximum probability. He can directly know the key. For other probabilities, he can still get some impossible value of the key and reduce the key search space. So by the way, V and V star are known to the adversary. Here is the illustration of the fault analysis result. Quite straightforward. Like the figures in the DPA and CPA, we plot the probability of values for the subtract bytes along the number of samples. So if you see the red curve, which is all 0, you know the value of V. If you see the blue curve, which converges to over 256, you know the value of V star. That is the core idea of original PFA. With enough number of ciphertexts, the red curve can be easily detected. Next, we explain our motivation and the main idea of this paper. Differential fault analysis is based on a transient fault model. So after the fault injection, it will propagate to the ciphertext along the fault injection location. As you see on the right, the DFA injects the fault into the 9th round of AES. The attack gets one exploitation of the fault leakage from 140 ciphertext. There are two facts here. On one hand, the fault injection will only affect the result of single encryption, and the recovery of the full key will require multiple encryptions. On the other hand, reducing the number of injections relies on increasing the injection depth, which leads to the increased analysis difficulty. What's more, the fault leakage only exists at point of fault injection. Therefore, the persistent fault analysis based on a different fault model is proposed. For the PFA, the adversary can inject faults before the encryption of block cipher, and the fault persists in multiple encryptions and disappears after the device is reset. This means one fault injection can exploit it multiple times during the multiple encryptions. But unlike DFA, PFA utilizes statistical methods for analysis. However, the original PFA in CHES in 2018 only uses the last round of fault leakages. In 2020, enhanced persistent fault analysis (ePFA) was proposed to take a further step to exploit the fault leakages in the penultimate round of AES. They have the same fault model as PFA. We can find the thief here is the attacker, who has the capability to analyze multiple rounds. In the figure, he can walk one more step to the left, but the constraints added by the ePFA are complex, as shown in the upright figure here. To explore the AES with multiple rounds of fault leakages, the constraints for ePFA need to be driven manually, and the deeper the round goes, the more complex it is, and it is nearly impossible to go deeper in the inner round. However, there are still many erroneous distributions of SBox output beyond the penultimate round, which do lay there and wait for the further exploitations. So these leakages in the inner rounds are what we call free fault leakages, which are like free lunches waiting to be grabbed by the thieves. In these fault leakages can be fully utilized. There is no need for additional injections, making it possible to break the cipher with only one injection. But there is no such thing as free lunch. Here are some reasons. First, it is difficult to manually exploit fault leakages from deeper rounds. Second, like ePFA, the deeper the rounds are used, the more constraints are manually constructed, and the complexity increases exponentially. So how can we easily have the free lunch? Let us recall the DFA. When DFA meets the deep rounds, the fault difference becomes increasingly complex along the propagation path, requiring a very complicated analysis. Instead, algebraic fault analysis is proposed, which introduces the algebraic technique and relies on the machine solver to cope with the complex fault difference. Therefore, we take algebraic techniques into consideration. Like the robots here in the figure help us taste the free lunch. But how to interpret those free leakages with algebraic equations is also never explored, which is the point of our presentation. Next, we take a look at the methodology of APFA. First, we abstract the round function of the SPN cipher, which contains three operations: substitution layer, the permutation layer, and the addition. The figure shows an example of analyzing the Aes intermediate round. The core idea of APFA is to find a general algebraic representation for position fault that is already injected. So the algebraic representation has two properties. First, it can connect the faulty output of each substitution layer, and the form of fault leakages are the same for each round. Second, the specific expression should not depend on those algebraic representations of next rounds. Otherwise, it will cause explosion. The fault leakages of each round are only related to the round key KR and the intermediate variable YR. Therefore, a single method of fault leakage exploitations can be used as follows. Line 1 here means that the output of for the S box will not be equal to the original value V. Line 2 means that the intermediate variable YR after AK contains the fault leakage. Line 3 here means that performing the inversive permutation operation PL on YR can exploit fault leakages. We can deduce the constraint on the right here, where KR is not equal to YR XORed with V. So the beauty of this equation lies in its simplicity. When applied to different rounds, the only difference is the round index R. There's nothing to do with all other rounds. In fact, each round of fault leakages has the same format, and how to describe them in algebraic representation is a challenge. So we can explore the nature of XOR operation. If A is not equal to B, it means A XOR B will not equal to 0. Then we can introduce an intermediate variable D, making it equal to the XOR sum of all variables in the fault leakage equation. And DI here is the I space of D. According to the nature of XOR, it means there must be an element in DI that is 1. So we can use this disjunction operation of SAT to achieve this target. In summary, with these two equations, we can exploit the fault leakages to remove Y XOR V from the long key search space. Here is our pseudocode. Finally, we take a look at application. So present is a lightweight SPN cipher. It uses a 4-bit S box. So the round function of present contains 3 operations. The first operation is a round key, which is relatively simple to express. As shown in these equations, the XOR value of each bit of the input, output, and key is 0. The second operation is P layer, which is the bit-based permutations. For the bit-based permutation, a single bit of output is only related to a single bit of input. This type can be used a permutation table TP here to describe the relation between the output and the input bits. The third operation is S-box layer, which is the operation involving the S-box. For the faulty S-box, after determining the fault location L and the fault value F, it is equivalent to knowing the truth table. So we can transfer the truth table into an algebraic norm form ANF first, and then later be re-transformed into CNF, and then fed into the general SD solvers. The LED cipher is shown in the figure, which is similar to AES. It's a representation. The round key is the same as present. So we divide the linear addition layer into the XOR with key called AK, and the XOR with the constant called AC. So next, the substitution layer of AD is also very similar to present, but the permutation table of shift rows is different, shown below here. Another permutation operation LD is based on the MDS matrix multiplications. Since matrix multiplications involves a multiplication operation over the finite field, the output bit may be related to the multiple input bits. So here is a table that shows the relationship. Then we talk about the skinny cipher, which consists of 5 operations: the constant addition AC, and the substitution layer, SB are the same as other ciphers, but the key addition of Skinny is different, which only performed the first two rows of the state matrix, and the MDS matrix multiplications only use a binary matrix. To review the fourth linkage of APFA, in general, it is necessary to perform an invasive permutation operation on the intermediate variables. However, it can be seen from the figure of the round function that only the constant addition AC between the substitution layer SB and the key addition AK. It means that the invasive permutation operation is not required when building the equation for the fourth linkage. This is one of the reasons why APFA is very suitable for Skinny. We also extend APFA to Feist-based block cipher L block. From the round function L block, it can be found that the distribution of the S box will be masked by the input of previous round, so the fourth linkages cannot be directly used. So we need to relax the fourth model. There are 8 different parallel S boxes in the SB of L block. Assuming a single fault has been injected into the one S box, SI, and the fault location is L. The adversary needs to increment the same plaintext twice, one for the normal inclusion and the other for the inclusion with the faulty S box. Thus, he can collect those ciphertexts that have not been accessed, the faulty S box, during the whole inclusion. And this means that the value of the input xi XOR the key ki is not equal to the fault position. Finally, we have a new constraint. Ki is not equal to xi XOR L here, which can be used by APFA. In our experimental result, a total of 112 ciphertexts are required to recover the complete key. In addition to the serial analysis, we implemented experiments on a PC. Here are our results. For lightweight SPM block ciphers, we only need to know more than 50 ciphertexts to recover the mask key, no matter which cipher it is. And APFA is not sensitive to the size of the key, no matter whether it is present or skinny. Increasing the key length will have no impact on the number of required faulty ciphertexts. Here are other results. The first figure shows the variations of solving time as we increase the analysis steps of present 128 with 40 ciphertexts. When fault leakages are sufficient to solve the mask key, increasing the number of analysis rounds does not reduce the solving time. Instead, extra time is used for the intermediate variables. The second figure is the analysis steps required by Skinny on the different ciphertexts. The slope change of Skinny is particularly obvious, and the required number of rounds increases faster when the ciphertext decreases. The 40 leakages that can be provided in each round is decreasing, and the relationship of deep rounds with the 40 ciphertext is getting weaker and weaker. For conclusion, in this paper, we provide a new direction for the subsequent analysis of PFA. First, we propose algebra position fault analysis as a new analysis method, combining PFA and AFA. Second, we apply APFA to a variety of lightweight block ciphers, such as present, LED, and skinny. Last but not least, we extend APFA method to the Feist-based block cipher L block in order to verify the generality of APFA. Thank you. Questions?
We may have time for a quick question. Someone have a question? Nope. On Zoom, maybe? No. I guess I'll take the opportunity to try to reschedule, and because we're running a bit late. So let's just thank the speaker again.
Thank you.
And the next talk will be given by Shivan Basin. So he will present SIPFA, I don't know how it's pronounced. He will tell us.
It's on, right? Yes. Okay. Good afternoon, everyone, and thank you for attending this talk. So in this work, I'll be presenting a joint work with colleagues from Iran. This is Nasur Bagheri, Sadeh Sadki, Prasanna Rava, and Hadi Soleimani. And actually, they started with this work, and like they asked me to present it, but it's a pleasure to present over here. So in this work, we actually try to extend persistent fault analysis to VSL ciphers. So first, I'll talk about basically a bit in detail how persistent fault analysis work. We had a like a quick presentation from Terry in the last one, but I'll go a bit more into detail and focus on why it is not applicable on VSL schemes out of the box, and then we come up with a solution. So fault injection attack, as we all know, like the main idea is that we have a chip, or a device, we try to push it into an unfriendly environment using different means, either something low precision or high precision. But since the device is not designed to work in those conditions, it will make some computation errors, and then we exploit those errors. Now, you can try to classify those fault attacks based on different, so the taxonomy can be quite wide. You can classify on the duration, what the fault is doing, or basically objectives like are you doing it for a key recovery attack or like bypass security check. So here we'll be focused on fault attacks classification based on duration. So normally, if we look through like several years of literature of fault attack, most of the work have focused on transient attack, transient faults. So transient faults are basically one shot. We go into the computation, we affect or fault one particular value, and then we come out and we let the rest of it compute correctly, or continue from there without any more effect. And if we look at differential fault analysis and like other fault analysis, most of them are basically based on this one. But we do have some work on permanent faults. These are, let's say, traditionally located to defects in devices, but of course it can be done by artificial means. And normally, like stuck-at faults or similar faults are classified under this condition, and there are some analysis, mostly statistical, that are used to exploit these ones. So with Terry, who was presenting the last talk as well, we had proposed this persistent fault analysis in just 2018. By persistent, we actually kind of classify a hybrid kind of a fault model which is between transient and permanent. So by persistent, I mean that we go in, we inject a fault, we let it stay for several encryptions, but we can still recover the system by either rebooting the system, or let's say resetting something, or let's say reflashing altogether the device. So the adversary model that we consider over here is that the block cipher, this is the first work where we implement a block cipher. It's a serial implementation, which means there's a single S box in memory, which is used by all the rounds and all the bytes or words, whatever. And we have this common S box. We inject a persistent fault in that S box, which means we change one value of the S box, and then we just feed in n plain text to it, and we collect n ciphertext. So since the fault is in the S box, when it is loaded to the memory, it will stay for all the encryptions, and all the rounds and all the bytes will be equally affected by the fault. So whenever that byte is used in the computation, we will see the fault. So the main idea is encapsulated over here. We take S box of present over here. So basically, we take this 10 value and we change it to an 8. Now, normally it's a bijective S box, so every value appear only once. But now, if we look at the distribution, 8 will appear twice and 10 will never appear. So now, when we do the analysis, what we see is like we can forget all the rounds that are in the algorithm. We only focus on the last round. So we have this in the last round, we have this S box and a key addition. And since this S box has a bias at the output, we will see that directly in the ciphertext. And this ciphertext will be just permuted by the value of the key. So therefore, we can simply recover the key. And we had basically if I have to explain it, let's say more in terms of how do we do the analysis. So it's a statistical analysis on the last round. We only require ciphertext in this case to exploit it. The fault changes one particular value in this box. And basically, we look at the expectation of that value. So one value should be missing and one value should be appearing twice as much. And therefore, we can have different strategies to exploit it. I think there's some font issue here, but we can either look at what is the missing value or what is the value which is appearing more often, or we can combine them as well. And in the first version, when we did this, like we look at how to determine the minimum number of ciphertext or the average number of ciphertext, and then we go with the we can take the classical coupon collector problem, and we can get how many ciphertexts are typically required. So, and if let's say X and X star are not known, this can be brute force, given that we know one plain text ciphertext pair over here. Okay, so we apply it on AES and present, and of course it works. Actually, so the key let's say selling point here was that, okay, we only have to trigger the fault equipment only once, but by collecting multiple ciphertexts, we can recover the data. And we have shown that this works on actually detection countermeasure, infection countermeasure, and we also looked at several public implementation of higher order masking, and we could actually exploit this. Of course, masking does not protect against fault, but when we saw at some of the implementation where lookup tables are used, actually masking at any order for certain implementations would be broken in actually the same number of ciphertexts as an unprotected implementation. And there were some follow-up works on this, which had made improvement to persistent fault. There was like a chain of work which was trying to reduce the number of ciphertexts required. So either by combining all the information using maximum likelihood. Also, there were works which were trying to exploit multiple faults, because what happens is when you try to inject a fault into an S box, I will show in the experiments later, it's quite likely that you might affect multiple bytes, but rather than one byte, and therefore how to exploit it. So even up to 16 bytes actually, and with a reasonable complexity, it was possible to do. And this last paper was actually presented this morning. Basically, one thing which we find common in all this work was that it was never applied to fiestal ciphers. So this we looked at the reason why this is the case, because for one of the work we were trying to apply it on fiestal ciphers and it was not working. And the main reason or the main challenge when we apply it to fiestal cipher is that normally fiestal, like a classical construction, you have this branch kind of a construction where you have the F function in between the two branches, and you mix the two branches in every round. So basically what happens is that this F is applying the S box, so you get the bias, but the second branch will actually mask the bias that is coming out in a fiestal cipher. So therefore, it is not possible to directly apply PFA on a fiestal cipher. And we actually looked at one work which was available on DES, but that was done in a chosen plain text setting, like when you cannot choose the plain text. And also in the last work, when you cannot choose the plain text, like you don't know you cannot apply it directly. Another issue with applying it on fiestal cipher was that unlike AES or present, which are common SPN cipher use, DES and triple DES have distinct S boxes. So you have 8 different S boxes. So this breaks the first assumption that I was talking about, that we have a common S box that is used in all the rounds and all the bytes. So this would increase the attack effort to attacking each S box individually in different campaigns. And also the S boxes are non-bijective. So therefore, when we look at those distributions, those do not apply anymore. So basically, what we found, like how we tried to solve this problem was to look at, instead of looking at the output of the S box, we moved to the input of the S box. But then we had to rely on ineffective faults. So this goes towards the line of CIFA, which was exactly doing that. So basically, at the input of the S box, let's say there is a value which is changed. And basically, what we look at there is that what is the probability that the cipher that a correct ciphertext comes, and if there is a like the probability that the correct ciphertext is coming is directly related to the number of times SBox is used in all the rounds, and that actually can be used to develop a distinguisher of the key. So again, like ineffective fault on X introduces the bias in the computation, which is then exploited for the key. And since it's a combination of these two techniques, so we also name it as a combination. Since it's beyond 5 p.m., like we will not talk equations anymore. I'll just show you like the classical example. So in the paper, you will find algorithms for key recovery for how we exploit it, and there are two different use cases. One is on a detection-based countermeasure, and the other is on a infection-based countermeasure. And we have shown it to work in two different attack models when you know where the fault was injected and to what value, and also in the unknown setting. And so these are like some simulations when done. So like in an unknown setting, we are able to actually distinguish where there's in which SBox and which value of the SBox the fault was detected. And then once we know that, we can actually directly apply the key recovery attack to recover the key. So for example, in DES, about 400 ciphertexts are needed to recover one part of the key. So to compare it with other works, we are the only work who is doing it in a ciphertext only setting, and like if the attacker has the liberty to attack individual S boxes independently in independent campaigns, the complexity is quite negligible. But of course, we need to run the same attack 8 times. But in the worst case, we can only inject one fault without knowing the location of the fault or the value of the fault, and with some offline complexity of between 2 to the power 40 to the power 50, we can actually recover the key. And the number of ciphertext, depending on the cipher, ranges between 3,000 to 7,000. We verified this attack on using electromagnetic setup. So we had we were working with this ARM Cortex M4 M4 device, and we took a public implementation of triple DES. So in this implementation, like on boot up, the S boxes are actually transferred from flash to the RAM, and this is the point we attack. Now the thing is that since the data bus is 32 bits, when we inject the fault, it's very likely that we will affect multiple bytes of the fault. So therefore, we had to calibrate the equipment so that we can find a single fault and then exploit it. So this was the ratio of single to multiple faults. So in the morning, actually, we had presented how multiple faults can also be exploited in block cipher in SPN ciphers. But actually here we were obliged to work on single faults only. So we had a short percentage of the total faults, but like if we just sweep through time when the transfer is happening, we found several locations with high repeatability where a single fault was possible. So in this case, we were able to get up to 80% of repeatability in terms of like finding position, knowing the position and the timing. We could actually recover the inject a single fault into any one of the SBox, any chosen SBox. So these are like the heat maps for the repeatability. And finally, coming to the conclusion, so like we tried to solve the challenge of applying it to VSL ciphers in a ciphertext only setting by mixing persistent fault analysis with CIFA, and therefore we have this SIPFA. We validated it on 3 different algorithms: DES, triple DES, and Camellia. And currently, we cannot handle multiple faults for VSL ciphers. The main reason is that the probability of having an ineffective ciphertext decreases when the number of faults in the SBox is high. So now, as a future work, we might try to look into solving this issue as well. Thank you very much. And if there are any questions.
Is there any question?
Often I would use a checksum on the S boxes. I mean, using that it's balanced. So I just take the XOR of all values, and if it's not 0, then I know something is going on, and so I don't give any output. Does the attack still work if you make checksums?
Sorry, can you please repeat the question?
I mean, usually I would make a checksum of the S box in the RAM to see that there are no faults. And
this is definitely like a countermeasure. Actually, in one of the previous
oh,
slides.
you're here. Good. I went to the laundry, dryer, to rush back.
Sorry. Yeah, so actually we already this is one of the way to protect it is like you need to have a check on the S boxes that are they correct or not. So the implementations we were looking at, we never found or we never found such an implementation available. But yeah, if you check it on boot up, of course, but what if the fault is injected later?
I mean, I would check it every time before I give anything out.
Yeah,
of the
in that case, of course, like the persistent fault can be avoided.
Okay, I think we'll go through the program. Oh, sorry. Okay, let's take the last one.
Hello. Yeah, thank you for your talk. I have a quick question about the motivation slide, I think, because you mentioned the issue with Feistel ciphers and then mentioned that the S boxes are not bijective. Well, this indeed, but these are not properties inherent to Feistel ciphers, right? If you look at SM4, the Chinese,
that is true. Like so, even for Camellia, that was not an issue, but for DES, that was an issue.
But would you say that the attack then mostly applies to non-bijective S boxes, etc., and not necessarily Feistel ciphers?
No, when we attack Camellia, it's actually a bijective S box.
Oh yeah, but okay, but
so it works actually.
Okay, fair enough.
But even if the S box is not bijective, so like by coming to the input, we are able to solve it. But for Camellia, we don't need that yet.
Fair enough. Okay, thank you.
Okay, let's thank the speaker again. The next talk will be given by Pascal Nazahel, and it's continuing the trend of how to pronounce concepts. So it's SynFi, I guess.
Thanks. Oh yeah. Okay, great. Thank you so much. It's my okay. So does not work. Perfect. All right, then. Thank you for joining my talk. My name is Pascal Nazal from Graz University of Technology, and today I want to present you our SynFi tool, which we use to do a pre-silicon fault analysis of open source secure element. It's joint work together with folks from Google, Low Risk, TU Graz, and also Lamar Security Research. So we already had an introduction to fault attacks, but again, so fault attacks are active physical attacks where an adversary basically injects one or multiple faults into a chip using some kind of fault injection technique, such as laser, clock glitching, or voltage glitching, or temperature glitching. Originally, fault attacks are pure local attacks, so we had to have physical access to the device under attack. We need to decapsulate the chip, we need to shoot with a laser on a chip, but nowadays we also can do fault attacks in software remotely, for example, Plunderwall, Clockscrew, and so on. What are the effects of fault? Well, usually at the electrical level, we basically observe some timing violations, but we also see transient voltage and current changes. However, typically we are more interested in actually modeling a fault at a higher level of abstraction. This is the bit level. So here we have either transient effects, bit flips, or permanent effects such as stuck at zeros or stuck at ones. What can we do with faults? Well, we can exploit the injected faults to, for example, manipulate the control or the data flow of either hardware or software. In terms of hardware, we, for example, can target finite state machines. We can here manipulate the control flow. But we also can manipulate the data flow by, for example, flipping bits and handshake signals in a processor or in a AES core. In terms of software, here we also have different possibilities to basically manipulate the control flow of software on a CPU. For example, we can inject faults into the program counter to arbitrarily jump in the program, or we also can basically flip bits in the interrupt vectors, also allowing us to hijack the control flow of software. We also can manipulate or skip instructions, for example, jump instructions or whatever. Now, what can we do against countermeasures? So basically what we do is we use some kind of redundancy. So either spatial redundancy or temporal redundancy. So we either have multiple copies of our circuit, or we're executing the circuit a couple of times. But we also can use some kind of encoding, which helps us to actually detect or even correct the effect of a fault. Where do we find these countermeasures? Well, usually we find countermeasures at security critical devices like secure elements. And one secure element I want to show you is the OpenTitan. You already heard it yesterday in the keynote from Dom. The OpenTitan secure element, where basically RTL, DV, software, firmware, and also the tooling is open source. So you can check it out on GitHub. And it basically is meant as a root of trust. So we have a key storage, we have AES accelerators, KeyMac, and so on. So really a full-fledged system here. And this is a secure element. We clearly also have countermeasures in hardware. So on the one hand, side channel countermeasures, but also fault countermeasures. And today I'm interested in, or I want to talk about the fault countermeasures here. And the question we had, how can we really make sure that the countermeasures, the hardware-based fault countermeasures actually work? What we usually do in hardware design is we do testing at the RTL model. So we write a test bench, we inject faults in the test bench, and we basically check whether the countermeasures we worked on, we built, are actually working or not. Problem is that all the results we gained basically at this level of abstraction is only valid at the RTL model. Why? Because after the RTL model, we're starting with the synthesis. Synthesis consists of a lot of steps, so several optimization phases, which basically try to meet area and timing constraints. And here we all know that optimization and basically redundancy could be really critical. So we cannot really know whether after the synthesis at the gate level netlist, our countermeasures are really working. What we also can do is we can basically map our design to an FPGA. We can do physical fault injection at the FPGA. Problem here is, again, it's a different technology. So if you're aiming for an ASIC, it's different technology. We're also using different tools. So we cannot really map one-to-one our results from an ASIC to an FPGA, from an FPGA to an ASIC. So finally, we can order pre-production sample or pre-engineering sample, do physical fault injection into the chip there. Again, this is really costly, time consuming. It's also quite late in the actual design phase of a chip. So our idea or our approach here is that we want to do the verification or the analysis of the countermeasures at an earlier stage. And this is after synthesis at the gate level netlist. So why do we need a tool for this? Another tool? Basically, we could argue that we can do this manually, fault injection in the test bench at the gate level netlist. Problem here is that basically the gate names and wires are mangled, so we don't really know where to actually inject fault. It's kind of hard to do this manually for the security engineers or hardware designers. We also could related work. Problem here is basically these tools impose some requirements on the netlist. So either they only support a limited amount of standard cells, or they don't support cycles in the netlist, or only basically what we also had the problem is that only fully flattened netlists are supported. Is it possible to adapt the design flow to a security tool? Well, not very likely. Why not? The design flow, the hardware design flow needs to work. So it's basically an interface between different stakeholders, project management, hardware designer, firmware engines, and so on. So it's kind of hard to change to have your changes in the design flow. Therefore, we really want to use design flow as working, and meaning also a tool which basically imposes some kind of requirements on netlists. We cannot really use that. So we came up with a new tool. Basically, SynFi works at the gate level netlists. Here we're supporting gate level netlists, which are either generated by closed source tools. So we tested with several closed source tools, but also with open source tools like Yosys. We also support common design patterns, such as cycles, and also non-fully flattened netlists and so on. And basically, SynFi can help you to analyze whether the fault countermeasures provide the actual expected security. This is the tool. So this is a block diagram of the tool. It basically consists of two phases, phase 0 and phase 1, which you see here on the right side. Phase 0 is basically the transformation phase, and phase 1 is injection evaluation phase. SynFi also needs some inputs. So the input 1, the most important input, is basically the gate level netlist. So this is really the gate level netlist, which just comes from the synthesis tool, from the hardware design flow, which we did not modify. We just need to convert our Verilog netlist into a JSON netlist. Afterwards, we also need the cell library. So here we're also supporting industry-grade cell libraries, which we're actually using in the OpenTitan project. And the third input is basically the fault specification file. What is the fault specification file? Well, here we need to define what kind of fault experiments do we actually want to conduct. So here we need to define what are the countermeasures, what circuit state do we have, and so on. We also need to describe the attacker. So what are the capabilities of a fault attacker? Here we need to define the number of simultaneous faults we can inject in a netlist. We also need to define the fault locations, so either specific gates, but we also can do an exhaustive analysis. So we can say, just do the work for us and have a look into the netlist. And then we also need to basically define the fault effects. So we want to transient effects, permanent effects, stuck at zeros, stuck at ones, and so on. Basically the tool now starts to go to the preparation phase, so phase 0. What we're doing basically here is that we're taking the cell library, which is a .lib format, convert it to a Python library so that we can use it in the tool actually. Then we are converting the netlist into a graph. Here we are using a multi-directed graph and also storing it in a temporary file, which we hand over then to phase 1. In phase 1, we are doing actually injection evaluation. So what we do here is that we are basically extracting the graph which we're interested in. So we just default affect the graph. And we're then injecting faults, either at certain locations, or we just do an exhaustive analysis. We're creating differential graph, which consists of the faulty and non-faulty graph. We're adding some input and output logic. And then we are finally transforming this graph into formulas, which we then hand over to a SAT solver. Afterwards, the SynFi tool shows you, are there effective faults? And if yes, where are these effective faults and what was the effect here? Now, what is an effective fault? Well, SynFi here supports two different fault effectiveness. The first one is, exists there a fault which basically allows us to change the input-output behavior without triggering the countermeasure. So this is the first definition we have here. The second one is we're interested, can we reach a certain security critical state, for example, a debug state of a CPU, using faults without triggering any countermeasure. So these are basically the two definitions we have here. Then we used basically this tool for the OpenTitan. So we had a look into the countermeasures we worked very hard on are actually working. So here we wrote dedicated threat models for each of the modules. And in our work, we analyzed mostly on the Aes, the Lifecycle Controller, which you already had yesterday, the IBEX, which is the RISC-V CPU, and some more generic primitives like counters, LFSRs, and so on. For the tool, we used the unmodified gate level netlist, which we extracted from the hardware design flow. We did this for the closed source flow we have, but also for the open source flow, which is basically Yosys flow. I want to show you some examples what we did. There are many, many more in the paper, but just some which I want to show you here. The first thing we did, we had a look into the handshake signals. So AES basically consists of set of handshake signals which control the data and control flow of the encryption and decryption. These signals are basically driven internally by some state machines, finite state machines. And here the attacker goal could be basically to flip a logical 1 to a logical 0 or the other way around to influence this data and control flow. Where do we have here the fault targets? Well, we, for example, can target the finite state machine, basically next state logic, state registers, output logic, but you also can directly induce faults in the control signals, the output signals of the FSM. Basically, what the tool showed here, if you have no protection at all, it's quite easy to flip a bit here and to manipulate the handshake signals. In order to mitigate this, we come up with a multi-rail approach. We call this multi-rail approach. What we did here is that we're basically encoding single bit signals into 3-bit multi-bit signals. So we have here a logical 1, for example. The first 2 bits of this encoded multi-bit signal are just the copy of this plaintext signal, and the last bit, the blue bit, which you see here, is the inverted of the plaintext bit. What we then do is we're basically instantiating redundantly the finite state machines. And each of these finite state machines operates on a separate bit of these 3 bits multi-bit signals. In the end, we're then combining these individual single bits together to a multi-bit signal. And what we do then is we use a checker unit to basically check whether the encoding is still valid or not. This allows us to detect up to 2 faults into the final state machines, manipulating these handshake signals. Now we had a look with SymFi. Does this actually work? So here we configured the tool to inject 3 simultaneous faults into the netlist. The goal was of the attacker, so this is a fault target. We want to manipulate the handshake signal from a logical 1 to a logical 0, for example, and our expected protection level was 3. So we need at least 3 faults to do this. What was the result here? Well, SymFi basically showed us that the protection level is only 2. What happened? The synthesis tool was really smart and said, okay, we have a 3-bit signals. 2 of these bits are always the same. So let's just compress it and we have a 2-bit signal in the end. So this was the problem here. Our solution, we are attributing registers here, which basically allows us to tell the synthesis tool, do not touch these registers in the end. And we again run SymFi to basically confirm the expected protection level. Again, another example, this is the Aes again, with some final state machine. And here we were encoding the state registers with some approach where we basically have a minimum Hamming distance of 3 between the different states we have in a state register. The attacker goal is, again, we want to manipulate the final state machine, enter a different state, and we're doing this by only targeting, for now, the state registers. Our expectation was, again, we have a fault protection level of 3, so we need at least these 3 faults to basically enter a different state, and we configured SymFi to basically inject up to 3 simultaneous faults. Again, the protection level we had here was 2. What happened? Yosys was really smart and thought, okay, we can save some area by applying some final state machine optimizations, basically reducing the security. Our solution for that, we need just to disable this FSM optimizations in Yosys, and this is clearly an area where security trade-off we have here. Next element I want to show you is the Lifecycle Controller. I guess Dom already showed you yesterday in his keynote what this Lifecycle Controller is. Just a summary, it's basically a critical element of the OpenTitan, which basically is responsible for transferring this secure element in different operational states, so either in debug state, production state, RMA state, and whatever. And here the attacker goal could be that we want to enter a security critical state, for example, the debug or RMA state, where we get full access to the chip. What can we do with it? How can we do this by using faults? We have here different fault targets available. I just want to show you here 2. We basically can bypass the token check to unlock this debug state, or we also can hijack the final state machine in the end. We configured SymFi to inject up to 7 simultaneous faults. The goal here was basically to enter a debug state from the production state. And again, we had a expected protection level of at least 3, so it should be really secure here. The result is basically we couldn't find faults here in this setting, either faulting the token comparison or the state register to achieve this goal here. So we basically showed that our assumption was correct and the lifecycle controller gives us the expected security in the end. Also, my last example, what I want to show you here is the IBEX. This is a RISC-V processor, basically 32-bit small processor. Here, the attacker goal is to manipulate the control flow of software by inducing faults into the program counter, and we basically can redirect the control flow arbitrarily in the program. What we did here is we had, in this example, a look into the instruction fetch pipeline, injected some fault in there. For the single core setup, so we only have 1 IBEX, we showed it was quite easy to actually fault here the program counter. But if you switch the dual core setup, where we basically have 2 IBEXs, we showed this SymFi tool that the expected protection level of 2 is actually given. With this, I'm at the end of my talk. Summary, what we did is we basically implemented and designed an open sourced SymFi, which is a tool which allows you to analyze the resilience of 4 countermeasures. And SymFi really supports standards libraries which are either generated by the open or closed source flows. We had a look in the OpenTitan and used both, so either our netlist generated with the closed source tools, but also with the users. For the evaluation, we had a look into several modules. We were happy to confirm the security of most of the modules. We just found some weaknesses in the AES, but we also, and this is a certain contribution, we improved actually designs. We introduced the multi-rail FSM and some other stuff, which we also reassessed using SymFi and also contributed back to the OpenTitan project. In this case, thank you for your attention. And if there are any questions, I'm happy to take them now.
So we have time for questions.
Hi, thank you for your talk. So in your case analysis, you talked about the goal of the adversary, right? So entering the debug stage or something like that. Do you have any notion in the tool for that? And if yes, how do you model that? Can you elaborate?
Basically, what you need to tell the tool is what kind of state do we want to enter. In case of a state machine, we need to say, okay, can we enter this state here? Or in the case of the lifecycle controller, can we flip this token comparison? So this is what basically needs to tell the tool. But you also see this in the paper, how this configuration actually works.
Okay, so you give just the final stage in your enumerate the final state that you want to achieve. And
yeah, exactly.
Okay, thanks.
Yeah, thank you. Question is, what is the problem with dealing with flat and netlists? You explained that in related works or state of the art, just work with the flat and netlist.
So just a problem we had actually, that our hardware design flow did not use always flattened netlists. So we had some black boxes there, and this wasn't supported by some of the tools. This was just a problem for us, actually.
But if it's a black box, then how can you do the simulation?
You actually can give a function for this black box, basically. So it's saying this black box does some function, and you can provide here the Boolean equation of this function, basically. So this is what we support here in our tool.
Okay, thank you.
It just was for us, yeah.
I think there was a question over there.
Hi, thanks for the talk. Can you say something about runtime overhead compared to normal simulation, maybe?
So we compared it to different tools. Or yeah, so basically what we did, so you find all the numbers in the paper. So we were able to run experiments on the roughly 3.6 kilogate equivalent. This took, depending on the number of simultaneous faults you want to inject, a couple of seconds. If you only inject one fault, up to hours. So this really depends on the number of faults you want to inject. So it's definitely not the fastest approach, and clearly.
Okay, no more question. Okay, so let's thanks the speaker again and all the speakers of this session.
So this is the end of the thing. We just want to let you know that 2 people fell ill yesterday. They've tested positive for COVID, and they haven't come in today. So just we said would let you know if anyone tested positive. So we have. To reassure you, the place you're going tonight is huge. I have been with very, very good ventilation. Even the locals are going like, yeah, I've never been there, but yeah, it's huge. Yeah. So it's very good ventilation. It's absolutely massive. But if you are feeling ill, we have some testing things on the main desk. But we'll let you know. There we go. I think that was it. Okay.
There's another announcement.
Well, it's related to this. I just wanted to remind you that, well, there's this social event tonight at 6:30. And there will be a group of us walking from the Peter de Sommer Aula at 6:15, and you can join us, or you can just go there by yourself. It's about a 15-minute walk. You should be there at 6:30.